And we consider now conservation of energy, taking into account the work done by friction. When friction is active, it's going to take energy away from the system. Now, the conservation of energy concept, we start with a supply of energy in kinetic and or potential form. We have an initial supply of energy. The work done by this non-conservative force, by friction, will be a negative number. Our supply of energy is reduced. That leaves us at some later time, time 2, with a mixture of kinetic and potential energies. And problems involving conservation of energy, you'll have to identify what the kinetic and potential energy is at the start. You'll have to identify the work done by friction and put that in as a negative number. And then you'll have to identify what energy is present at the end, whether it's all kinetic or all potential or a mixture of the two. That's the general outline of how you solve problems in the topic of conservation of energy. An example here of conservation of energy, we have solar energy coming into the panels here. The solar energy is converted into electrical energy at the solar panels, and then that electrical energy is in mechanical energy of the propeller blade pushing on the wind, and the plane is able to fly. Not all of the solar energy becomes mechanical energy of the propeller, of course. There's friction in the motors. There's some loss of energy being converted as the sunlight comes in. It's not all converted into electricity, but it's an example of energy changing form. So let's try a problem here with conservation of energy. You have a block of wood, 0.8 kilograms. It's on a horizontal table, sliding across. We have a kinetic coefficient of friction. Won't bother to trick you up by putting in the static coefficient here because the object's sliding, so it's obvious we need the kinetic coefficient. So 0.22. We start with a velocity of 1.3 meters per second, and the wood is going to travel 27 centimeters. At that time, you're asked to find the velocity of the wood. So how could we go about this with the energy concept? Well, on a horizontal surface, we can say for mgh, the h value is 0 at the start, at the end. If you say the h value is 1 meter at the start and h value is 1 meter at the end, the net effect will be the same. The potential energy is making no contribution to this problem. We've got the same number on both sides. We might as well let that number be 0. So I'm choosing h equals 0 of the potential energy calculation, mgh. Let h be to 0 at the table. Well, we do have an initial kinetic energy, and 1/2 mv squared gives us the kinetic energy, so 1/2, 0.8 kilograms, 1.3 meters per second squared. Here is our work done by friction. We have the coefficient of friction, 0.8 times 9.8 gives us the normal force. So this is the force of friction acting over 0.27 meters, and we don't have to find a component of the force of friction. It's always directly opposite the velocity, directly opposite the displacement. So we have the full 0.27 meters. And when we're asking this at the end, we've already observed here there's no potential energy at time 2, at position 2, whatever you want to call it. We have 1/2 mv squared. Now take a look at these three terms. And you'll notice that the mass cancels. It doesn't matter what the mass of the block of wood is. So the 0.8s are everywhere here. They cancel off. So I've calculated here, not including the 0.8. Now this is not joules, because I don't have the 0.8 kilograms as part of the calculation. It's just a number with consistent units. We're in the standard metric system. So 0.845 for the first term. You ought to verify that. The term involving friction, 0.582. Equals 1/2 v squared. Again, the m is canceled everywhere. And I found 0.725 meters per second. At least it's slower. It started at 1.3 meters per second. I don't have a good way to judge if this is a reasonable answer other than it's less than the starting velocity. It should. Energy took away energy, or supply of energy, and we have less energy after friction does its work on the object. So that's conservation of energy situation where the potential energy did not make an input. A little comment on efficiency. Efficiency is measured by work done by a system divided by the energy put into the system. Autos are interesting. Very high efficiency, 0.3 or 30%. So if you're going to the gas station and you put energy that has a value of $40, energy of gasoline, $40 into the tank, what's the value of the work done? This formula is very flexible. The work can be measured in dollars and the energy in dollars, or the work in joules and the energy in joules. But let's do it in dollars here, a little more dramatic, more real. So efficiency times the $40 that went in, that's $12 of work we get out. We pay for $40, we get $12 of work. Not a great bargain. And where is the missing $28? Out the exhaust pipe and other heat losses from the engine, the radiator, losses due to friction. That's reality. And it's even worse for the average car with an efficiency less than 30%. Another example of conservation of energy, going in the roller coaster ride. If we go over the hill with a very small velocity, nearly zero, but we got to be moving to get over the hill. And we go down, obviously we're going to pick up speed as we go down the hill, and there's an energy calculation for this. So let's put this with some numbers. So the height of the first hill, 25 meters, and let's go ahead and say the velocity is 0 at the top of that first hill. We want to know the velocity at the bottom of that first valley where h is equal to 0. We have a certain mass for the car and the riders, and we're going to claim that the system loses 8,000 joules of energy to friction, the work of friction. I'm just guessing at a number there, that 8,000 joules of energy lost to friction. Well, conservation of energy, we have 1/2 mv squared, 0 kinetic energy at the start. At the top of the hill, we said the velocity was nearly 0. mgh, mass of the car, acceleration due to gravity, the height above our 0 point, so mgh, our potential energy. Here's the work done by friction. We lose energy from our supply, and then 1/2 mv squared and 0 potential energy at the bottom of the valley. I'm setting h equal to 0 at the bottom of the valley. Can I cancel off the 520 kilograms? I see it here, I see it over on the left side in the potential energy term. The answer is no, because that 520 does not appear as a separate factor here in the 8,000. So this time we have to keep the 520, and mgh, we have this many joules. That's our supply of energy at the top of that first hill. We lose 8,000, and 1/2 times 520 is 260. To solve this, I hope that you'll come up with 20.4 meters per second. Ask your instructor if that does not happen. Power has a simple definition. Power is work divided by time, and then this would be the average power. And then an instantaneous power, we can take force times velocity. We'll save that for future discussion. Our main concept here would be the conservation of energy. We have a supply of energy in kinetic and potential form. The work done by friction is a negative number, takes away from our supply, and then we have a final amount of energy, kinetic and potential, at the end of the problem. So practice more with that, keep reading, and ask some questions.